You know, the surface of our planet feels pretty solid, right? But it's actually in constant, slow motion movement, shaping and reshaping the continents and oceans over millions of years. Today, we're going to dive deep and explore the incredible forces that are at work, from the deepest ocean trenches all the way to the highest mountain peaks.
See, the Earth isn't just some static ball of rock. It's a living, breathing, dynamic system where new land is literally born from volcanic fire. The very ground under our feet is on a slow but absolutely relentless journey. It's all part of a geological dance that's been going on for billions of years.
And you might think, well, it's the coastline, obviously. But the real division is so much more fundamental than that. The answer lies deep, deep beneath the waves, baked into the very foundation of our planet's crust. Okay, so let's get into it. The first big clue is something we call Earth's bimodal surface. It's this clear separation between the high-standing continents and the really deep ocean basins.
Now, what's so fascinating about this chart is that it's not just a smooth slope from the top of Everest to the bottom of the Mariana Trench. Not at all. Instead, you see two very distinct levels. There's one peak for the continents, which on average sit about 840 meters above sea level, and then there's another, much bigger peak for the ocean floors, which are on average a staggering 3,729 meters below the waves. In fact, if you add up all the continents and all the islands, they only make up about 29% of the Earth's surface. They're basically just big islands standing high and dry in these vast ocean basins, and believe me, that is not a coincidence. No, that two-level distribution isn't random at all. It's the direct result of a simple fact. Our planet's surface is made of two fundamentally different types of crust. So on one hand, you've got the continental crust. It's really thick, it's ancient, some of it is almost 4 billion years old, and it's made of lighter rock, mostly granite. But then you have the oceanic crust, and it's a whole different story. It's thin, it's incredibly young, geologically speaking, at less than 200 million years old, and it's made of a much denser, darker rock called basalt. And this image, it shows you exactly why that matters. It's a principle called isostasy. Just think of it like putting a big block of wood and a small heavy stone in water. The less dense continental crust, at about 2.8 grams per cubic centimeter, literally floats higher on the semi-molten mantle beneath it. Meanwhile, that denser oceanic crust sinks lower. That's it. That's the fundamental reason continents are high and oceans are deep.
Okay, so we've got these two different types of crusts. But what actually gets these massive plates moving in the first place? Well, the answer is the planet's internal heat engine, a process we call plate tectonics. You see, the planet's entire outer shell, what we geologists call the lithosphere, isn't one solid piece. It's actually a giant jigsaw puzzle made of about a dozen major plates, and they're all slowly drifting across the surface at a rate of about 1 to 10 centimeters a year, which is, believe it or not, about the same speed your fingernails grow. And the engine that drives all this incredible movement, it's called mantle convection. The best way to picture it is like a giant pot of water on a stove. The incredible heat from the Earth's core, we're talking over 5,000 degrees Celsius, creates these super slow-moving currents in the mantle. Hot material rises, cool material sinks, and this process drags the rigid tectonic plates along for the ride, kind of like rafts on a slowly churning river of rock. So let's look at what happens at the edges, where these plates actually meet. These are the plate boundaries, and this is where pretty much all of the geological action on our planet takes place. And really, it all boils down to just three main types of interaction. Plates can pull apart from each other, that's a divergent boundary. They can smash into each other, a convergent boundary, or they can just slide horizontally right past one another, which we call a transform boundary. So, at divergent boundaries, plates are being pulled apart by these huge forces. This creates a gap that allows hot magma from the mantle to well up, cool, and form brand new crust. The most amazing examples of this are the massive mid-ocean ridges, which are like these giant volcanic seams running all across the ocean floor. This is literally where new planet's surface is being made. These enormous underwater mountain ranges are sites of constant volcanic activity, and they are continuously adding fresh basaltic crust to the ocean floor, causing it to expand. All right, now for the real drama, convergent boundaries. This is where plates are crashing together under unbelievable pressure. This is where old crust gets recycled, and where we see the most powerful geologic events on the planet, like massive earthquakes and really explosive volcanoes. And what happens in the collision really depends on what's colliding.
So, when dense oceanic crust hits lighter continental crust, the ocean plate always dives underneath. That's a process called subduction, and it creates deep ocean trenches and chains of coastal volcanoes. When two ocean plates collide, one subducts under the other, and you get these beautiful arcs of volcanic islands. But when two continents collide, oh, something truly spectacular happens.
The Himalayas are the perfect example. About 55 million years ago, the plate carrying India slammed into the Eurasian plate. Now, since they're both low-density continental crust, neither one was going to subduct. The only place for all that rock to go was up. It just crumpled and folded and was forced skyward, creating the world's tallest mountains. And you know what? That process is still happening today.
And finally, we have transform boundaries. Here, plates aren't creating or destroying crust. They're just grinding past each other. This motion builds up a tremendous amount of stress. And when that stress is released, you get powerful earthquakes, like the ones along the San Andreas Fault in California. But because there's no subduction or rifting, you typically don't get any volcanoes.
So all this activity, this creating, colliding, and grinding, it directly shapes the type of coastline that we see around the world. Geologists call this the continental margin.
An active margin is, well, active. It's also a plate boundary. Think about the Pacific Ring of Fire. Places like the coast of South America or California, that's where you find all the geological action. Earthquakes, volcanoes, a really narrow continental shelf, and a deep offshore trench. In complete contrast, you have a passive margin, like the east coast of the US. It's not on a plate boundary. It's geologically quiet, with a really wide, gently sloping continental shelf where tons of sediment builds up over millions of years. Now, when you put all of these processes together, the creation, the movement, the destruction, you get one continuous, planet-shaping cycle, the cycle of seafloor spreading. And this is the key to understanding why oceanic crust is always so young.
So here's the crucial takeaway. The ocean floor acts like a giant conveyor belt. New crust is constantly being born at the mid-ocean ridges. It then travels across the ocean basin for millions of years until it finally reaches a convergent boundary. There, it gets consumed, diving back into the mantle at a deep-sea trench. It really is a grand planet-shaping recycling program. This constant motion, all of it driven by the Earth's incredible inner heat, is just a powerful reminder that the world we see today is just one single snapshot in a geological story that's billions of years in the making. The silent, slow dance of the plates is forever reshaping the face of our world.